Hi student, let's discuss about algorithm analysis. So what is the need of analysis of an algorithm? So actually the need of algorithm of analysis is to estimate the time complexity of an given program. When we convert an algorithm to program and we run it, it takes some time to execute that, right? So to calculate that time we use some notations that is called there are three notations, which is big O, omega and theta. So we need to roughly estimate how much time an algorithm takes to execute. So that is called algorithmic analysis. If there is no need of analysis of an algorithm and estimating the time complexity that it takes to execute a program, then it will be very difficult that some program might take hours and some very large programs might take years and years. So it is very important to analyze an algorithm when we write a code. So as I said, there are three notations to analyze an algorithm. So one is, we call it as big O, other one is omega, and the other one is theta, and the final one, it is not used much, but we theoretically it is called small o. Here it is big O and here it is small o. So let's discuss one by one briefly. Here by the definition we can say T of n is equal to big O of f of n if there are positive constants c and n such that the main thing is this one, T of n is less than or equal to c into f of n when n is greater than or equal to n naught. This is of big O of n, which represents T of n is less than or equal to c into f of n, which says that the growth rate of T of n is less than or equal to f of n. And the second definition, omega, represents that T of n is greater than or equal to c into g of n. Yeah, T of n equal to omega of g of n says that when it happens only when T of n is greater than or equal to c into g of n. Okay, so here we can say that the growth rate of T of n will be greater than or equal to growth rate of g of n. And the third one is T of n equal to theta of h of n, which says that the growth rate of T of n is equal to growth rate of h of n. Here we can see that there are equal to conditions in both the cases as well. So if and only if T of n equal to big O of h of n and T of n equal to omega of h of n, this condition only gets accepted when these two conditions are got satisfied. Okay, now let's discuss about T of n equal to small o. Here it is called big O and here it is called small o of P of n. Here we can say that in big O case, T of n is less than or equal to c into f of n, but in this it is strictly less than, T of n is less than c into P of n, right? Yeah, less formally we can see it as T of n is equal to small o of P of n if T of n is equal to big O of P of n and T of n is not equal to theta of P of n. This says that T of n not equal to theta of P of n means it is, these growth rates like T of n and h of n these growth rates are not equal. So this is what we need in small o, right? There shouldn't be any equality. So these both conditions should get accepted. It is a kind of mathematical formula, but in case of definition it is like T of n is strictly less than c into P of n. These are the notations we use. You might be getting a doubt that if we had these many different kinds of notations, what we'll be using and why we'll be choosing that. And yeah, we'll be choosing theta because big O is called upper bound, omega is called lower bound, theta is called average bound, and it is called strictly upper bound. It is called a loose upper bound. We can call this as loose upper bound, which yeah. Now the most thing we use is average bound, which is theta, because it estimates the exact, which is equal growth rate of an algorithm. It estimates exactly how much it estimates the exact time complexity of an algorithm. So that is why we prefer theta. But you might be getting a doubt that what is the need of big O and omega. So big O is, there will be many cases in which we we can't be able to estimate the exact time complexity of an algorithm. Then in that cases we will be estimating like upper bound and lower bound of that algorithm by doing some mathematical calculations. So in that case we will be using big O and omega. So to avoid all this, yeah, and you might be getting a doubt that we can estimate either lower bound or upper bound. Why we need lower bound and upper bound? So in this we prefer upper bound, because when we analyze an algorithm in the upper bound case, we will be getting time complexity which is somewhat more. Then let's take a real life example. When we want to execute a program in a computer, before executing that program, if we calculate a time complexity, and based on the time complexity we will be changing the hardware. And if we estimate the time complexity lesser, which is lower bound, then we feel that this hardware will be sufficient for this program, and after executing that, the real time complexity which will be higher, then the program and hardware might got crashed. If we estimate somewhat if we estimate somewhat higher, which is upper bound, then we take care about the hardware and we feel that this hardware won't sufficient for this program, and initially only we try to replace that hardware for this program. Then there will be a smooth flow in the executing of program. So that is what we estimate time complexities in big O notation. So generally the main thing we will be using in algorithm analysis is big O notation. Yeah, so this is what the notations thing. And coming to how we compare here we are discussing that t of n should be less than f of n, t of n should be greater than g of n, and how we compare them. Do we compare directly? If f of n is less than g of n, then it is this growth rate is f of n growth rate is lesser than g of n? No, we won't do like that. We compare relative rates of their growths. What is the f of n growth? What is the growth of g of n? Then we compare them relatively. We don't compare them independently. So let's take an example. Here one function is 1000 into n, the other function is n square. Now we need to estimate what is the which function is having higher growth rate. As we feel when we see 1010 looks higher than n square, so we feel that 1010 might be having a higher growth rate, but it is false. We can't do like that. If for values n less than 1000, 1010 growth rate is higher. If we give n equal to 900, then it is 1000 into 900, but it is 900 into 900. So here 1010 is 1000 into 900 is greater than 900 into 900. But in case of n greater than 1000, for n equal to 1000, these both are equal. In case of from starting to n, if we start from n greater than 1000, then n square growth rate is much higher than 1010. So with that conclusion, we can say n square is having higher growth rate than 1010. If you have doubt, you can refer to this formula. These two lines says the calculation required for that. So if we still not get that, we can plot the graph. So if you plot like this, the x square graph, n square graph will look like this, and 1000 y equal to 1000x graphs will look something, it will look somewhat like this, or y equal to 1000x will look something like this. And after certain point they need to meet, right? So after meeting point, it continues in the same way, but the growth rate this point is 1000. So after 1000, the growth rate of n square function is very much higher than the 1010 function. Makes sense, right? So if we have any confusion regarding this, we can plot the graphs of 1010 and n square and we can compare them. Now if we discuss somewhat in theoretically, the definition says that here in case of big O notation, if we consider that big O notation, that is, if we consider this formula which is t of n is less than or equal to c into f of n, here it says that t of n is, the growth rate of t of n is less than or equal to the growth rate of f of n. In case of the second definition, which is t of n is equal to big O of g of n, then the growth rate of t of n is greater than or equal to growth rate of g of n, which is lower bound. The third definition is t of n equal to theta of h of n. Yeah, it is pronounced theta as we discussed. It says that growth rate of t of n equals to the growth rate of h of n. In case of fourth one, which is very much similar to the first one, except then it is strictly less than. Here we can see that the growth rate of t of n is less than, but in case of big O it is less than or equal to. In case of small o, it is only less than the growth rate of p of n. So this is how the theoretical definitions look like. Let's somewhat go to practical in case of what is upper bound and what is lower bound. Yeah. So here if we see t of n equal to big O of f of n, then we discussed that the growth rate of t of n is less than f of n, right? So f of n growth rate is higher than t of n, then we can say f of n is an upper bound of t of n. This line is important to understand. F of n is an upper bound of t of n, right? Yeah. Now in case of f of n equal to omega of t of n, we can say that t of n is lower bound of f of n. Based on the formula, we will be saying that f of n is greater than or equal to t of n, then f of n is greater than or equal to t of n, then f of n growth rate is higher than t of n. In this case, then we can say t of n is lower bound of f of n, right? You need to understand this one, this upper bound and lower bound here. Let's see some practical examples. As an example, if we consider n cube and n square, we can say that n cube's growth rate is faster than n square, but because it is a cubic function, it is a quadratic function. So we can represent them n square equal to big O of n cube or n cube. Yeah, we can represent them n square equal to big O of n cube. In the same way, n cube equal to omega of n square. So you can get this with these definitions. If you go through the definition once, you can get this exactly. Yeah. Now here if you see f of n equal to n square and g of n equal to 2n square, these growth rates are equal. You might be getting a doubt that here the coefficient is 1, here the coefficient is 2, but how can we say the growth rates are equal? So it doesn't the growth rate doesn't depends upon the constant values, it depends upon the variables, variable equation. So we can eliminate constants. We will be discussing this point in the further pages of the book. See, here we discussed n square equal to big O of n cube. So it can also be considered if g of n equal to 2n square, then we can say that g of n equal to n power 4, g of n equal to n cube, g of n equal to n square, all these functions should be greater than or equal to this n square. The n power 4 growth rate should be greater than or equal to n square, n cube growth rate should be greater than or equal to n square, n square growth rate should be greater than or equal to n square. So it accepts all the conditions. We can represent them in any notation. Then you might be feeling how can we exactly say that? So that is why we call it as tight upper bound. So if we consider n power 4 is not a tight upper bound to n square, n cube is also not a tight upper bound to n square. If we see n square is a tight upper bound which is very much close to 2n square, right? So we represent technically this one as the best option to choose. Okay, so as these both are similar, we can say g of n equal to theta of n square. Now there are some standard functions. Here we can see that big O of n power 4, big O of n cube, big O of n square. In the same way, there are some standard functions big O of. So we can see if it is big O of log n, it is logarithmic. If big O of log square n, it is called log squared function, which is if it is big O of n, then we can, for simplicity I am using big O notation here. If it is big O of n in terms of big O of n, then we can pronounce it as linear function. It takes linear time complexity. If it is n log n, it is not mentioned exactly here, we can say it as linear logarithmic. Okay, by combination of n and log n, we can say it as linear logarithmic. If it is n square, it is quadratic. If it is n cube, you can say it as cubic. If it is n power 4 like that, we can say that polynomial with power k. Yeah, we can say like that. And in case of 2 power n, it is exponential growth, right? So these are some standard growth rates with that terminology. Now there are some rules while we estimate this. If we add two functions like t of n plus t1 of n plus t2 of n equal to big O of f of n, like consider t1 of n equal to big O of f of n, t2 of n equal to big O of f g of n. If we add them, it will be like big O of f of n plus g of n, but we don't represent them as it is. We consider the higher value. So that is why to represent the higher value, we take it as big O of max of f of n and g of n. So we consider the max only. We don't take f of n plus g of n. Because it is addition, we consider the max one. In case of multiplication, if t of n into, like for example, to prove this, if f of n is n and g of n is n square, then is it better to represent big O of n plus n square, or is it better to represent big O of n square? So as we are taking the upper bound, it is better to represent big O of n square as this one, which is max of n comma n square, that is big O of n square. In case if we are multiplying this, let's consider we are multiplying this, then in that case it changes to n cube, right? So then we will be doing big O of n cube. We don't take here maximum or minimum like that. It will be like after multiplying, it will be turned into single term. It is big O of n cube. Make sense, right? Yeah. T of n is we discussed that polynomial with degree k. It is big O of n power k, right? And there is another logarithmic term here with this we call as logarithmic, and if it is square, then it is called log squared. If it is log power k, then we can estimate it to big O of n, but the exact is, if it is like log per k n, then we can estimate them to k log n. Okay, we can estimate it to k log n. So it is k times log n. Okay, we can estimate it like this, or it is somewhat similar to big O of n. As per the line mentioned in the book, it is big O of n. Okay, now see, we discuss about the constants value. It is very bad style to include constants or lower terms inside a big O notation. Yeah, what are constants and lower terms? If we consider plus here, this is the this is having higher growth rate, this is having lower growth rate. This one is lower, this one is higher. Now it is not good to include the lower terms as well in the big O notation. So that is why we exclude this, and we only insert n square one. We only consider n square one. That is of neglecting lower growth rate functions and including only the higher growth rate functions. That is enough. That is why we are taking max. So in case of what you might be asking, what is constant? So in case of 2n plus 3 example, so here we can exclude this. There is no growth rate here. It is of constant. So in case of 2n, 2 is a constant. 2 doesn't affect the growth rate. Okay, 2 doesn't affect the growth rate. So it is a constant. So we can neglect it. We can neglect this one. So neglecting constants looks like big O of n. It is simplified to big O of n. Okay, it belongs to big O of n. That is what this line says. Lower bound terms can generally be ignored and constants can be thrown away, which means we don't need to consider it. Yeah, and now you might be getting another doubt as well, that how can we compare growth rates if we get functions like this, which is f of n is n into log n, g of n equal to n power 1.5, right? So in that case, decide which of f of n grows faster. Now for simplicity, we can separate f of n to n log n, g of n to n into n power 1 by 2, which is 0.5, right? So in this commonly we can see n and n. So now the thing we left is we need to only compare n power 0.5 and log n. It is obviously known that which is equal to square root of n and log n. We obviously know that square root of n is will be having higher growth rate than log n, right? Make sense? Which is in terms of n only. So n grows faster than the power of log. That is why g of n grows faster than f of n, which is n power 1.5 grows faster than n log n. Okay, so you can read this statement once, and you can read all this theory. If we start discussing these three, it will take really a lot of time, and which doesn't make any sense. We need to be good at practical, how to analyze, and we need to be good at how can we analyze and how can we estimate the time complexity for a given program. Yeah, so now we will be diving into somewhat more practical. In order to analyze algorithms in a formal framework, we need a model of computation. So we consider that algorithm as a model. So our model has standard some simple instructions such as additions, multiplication, which takes constant time. We call it as big O of one time. Here constant time is called as big O of one time. I think we need to, yeah, C. It is C, which means constant. Big O of C is nothing but big O of 1 only. This is called constant time complexity. These are constant operations. These such as addition, multiplication, comparison, assignment takes constant time operation. In case of, if we compare like sort an array, or if we want to multiply two matrix, it won't take constant time up, because it contains many assignment operators, it contains many multiplication, it contains many addition operators. Summing up all those things, and based on the size of the input, we estimate the time complexity, right? So there might be a confusion that if the memory is less, then the time then it might take somewhat more time to compile, and if the memory is more, then it might take somewhat more time to compile. So to avoid all those confusions, we take as infinite memory, then there won't be any change in time complexity based on the memory size, right? So that is why we consider infinite memory here. And now the most important resource to analyze is the running time. Yeah, so there might be several factors depending upon the algorithm, to analyze the algorithm and to estimate the time complexity of an algorithm, and the most important thing is running time. So this running time depends upon several factors like compiler, which compiler we are, whether we are using online compiler or offline compiler. So generally any compiler, a compiler in a good computer executes 10 power 9 instructions per second, right? So each instruction is, you can call it as constant time. Each instruction takes single unit of time, and this runtime depends upon compiler, this runtime depends upon computer hardware used, and but we can't exactly say that on which compiler, on which hardware we are using. So we generally compare based on theoretical, which is called algorithm analysis, that we are learning now. So we compare based on theoretically. The other main factors are the algorithm used and the input of the algorithm. So to analyze an algorithm, we are saying that big O of n square, big O of n. What is n in the what is n in big O of n? What is n in big O of n square? N is nothing but the size of the input into the algorithm. So here you can see, if we are taking an array as an input, then the size of the array is n here. So based on that, we say the time complexities or the analysis is big O of n, or big O of n square, or big O of n cube. So the other main factors are the algorithm used and the input of the algorithm. Makes sense, right? So, and every time we analyze an algorithm, we consider into three different cases. One is best case, other one is average case, and the third one is worst case. The best case happens very rarely. We calculate it rarely. Average time complexity we calculate is somewhat frequently, not much frequent, but the most important is worst case time complexity. You might be asking, there are three kinds of, how can you say worst case time complexity is more important? So because we estimate worst case time complexity for any kind of input. So you might be if I write a program for small size of inputs, then it will be running fine with less amount of time for small amount of inputs. When I given a very huge amount of inputs, then it won't be executing, it might be crashing, or it might take some long hours of time to execute it. So to include all these worst cases, worst scenario, whatever the input size may be, based on the given constraints in the program, we estimate the worst case time complexity. So finally we can decide, definitely that growth rate, the runtime of that, or the analysis or the time complexity of that program will definitely be less than or equal to the worst case time complexity, because we are considering all the edge cases, corner cases, and the worst cases which we need to consider while executing this program. So that is of worst case time complexity. definitely the executing time of that program will definitely be less than or equal to the worst case. Okay, yeah, you can get that program, I mean that from this paragraph what we discussed now. So yeah, here we occasionally the best case performance of an algorithm is analyzed. Yeah, we discussed it. Now average case performance often reflects the typical behavior. Yeah, often we consider average case time complexity as well. Now worst case performance represents a guarantee for performance on possible input. Okay, so worst case performance represents a guarantee for performance, for good performance on any possible input. Here it is not depending upon the size of the I mean it is not depending the time I mean the analysis or the behavior is not varying based on the size of the input. So it is whatever might be the input size, the behavior won't cross the worst case time complexity given. And if a program is running much more slower than the algorithm analysis suggests, there might be an implementation efficiency. So we might be here that the C++ runs somewhat faster, or Java, I mean Python runs somewhat slower. Yeah, these are difference between languages, and it also depends upon how well we implement that code, how well we convert that algorithm into code and we execute it. If we write an inefficient code with using so much number of variables, much number of computations, so that code will take definitely useless computations, then that code will be taking much time it will take much time to execute, and it is called, we might estimate that this program having worst case, a very high time it is taking very high time to execute. So it depends upon the how well we also convert that algorithm into code and the implementation efficiency. So it is, if we are performing an efficient performance while implementing, then it also results in the high time complexity. Okay, so here we can see there is a one reason for considering worst case, because one reason for this is the provides the bound of all input, including particularly bad input, worst cases, which can average analysis does not provide. So if we estimate the average time complexity of an algorithm, then it won't be estimating the time complexity when we consider the large size inputs. So worst case will considering all cases of and all kinds of inputs, and it gives the final time complexity. That is what theory. Now we understand with some examples. Here is also practical times which are executed in real life, and these are some times in seconds. This is the maximum subsequence sum problem. Here subsequence means contiguous subsequence, we can call it as maximum subarray sum. Yeah, if in this example the maximum subarray which is having highest, the subarray which is having highest sum is 11 minus 4 13, which is sum up to 20. Okay, so this is the subarray having highest sum. Subarray means contiguous subsequence. Okay, now there are different ways to calculate it. There is a times which execute in n cube, there is a program which executes in n square, there is a program which executes in n log n, there is a program which executes in only n. There are three different kinds of approaches in an this is very much inefficient, right? This is also inefficient, this is somewhat efficient, but linear time is most efficient. Let's compare their executing times with varying input. See, this is big of n cube, this is big of n square, this is n log n, this is big of n, which is cubic, quadratic, linear, logarithmic, and linear. Now when n equal to 100, these are the executing time, run times in second, it is measured in seconds. So this is how it took. But when we multiply the input size with 10, now it became from 100 to 1000, it will multiply 1000 times. When we multiply input size with 10, the n cube multiply 10 cube times. If you multiply 10 with input size, it is multiplying 10 cube times. It is growing in a cubic way. For you can see a drastic change from this to this with increasing only 10 with increasing the array sizes to 10 times. But in case of n square, it is if increase the if we multiply, if we increase the input size 10 times, then it is increased 10 square times, right? In case of n square. In case of n log n, if we increase it 10 times input size, it increases 10 log n times. Makes sense? 10 log n times, which is 10 log 10, which is very much closer to 10 only. Yeah, if we increase input size 10 times, then the linear time complexity is also executed 10 times only. You can see a difference there. When we multiply this 100 with 10, we are getting 1000. In the same way, we are just multiplying this with 10 and we are getting this one, which is moving one decimal point towards left side. Okay, so there is only, if we multiply the input size with 10, the algorithm is also executing in the same way, I mean in the same proportion. So it is the best case time complexity. When the input size is increased to 10 power 6, then it will be definitely taking very huge amount of time, right? This is though that is why it is provided not available. In case of logarithmic and linear, we can see that these are the times that are provided. Here you can see that the times given do not include the time required to read the input, which means we need to take the runtime input of all the array elements and we need to store it in an array, right? So this time does not include this read time, I mean read input. Now if we compare this graphically, this represents cubic, this represents quadratic, this represents linear logarithmic, and n log n, this represents linear. Now we can see after this crossing point, I mean till this point, n log n is n log n is having higher growth rate than quadratic. But after this point, which is around 45, after 45, n square is having higher growth rate than n log n. So we compare, we can say that finally n square is having higher growth rate than n log n, right? We compare for large inputs, so we take consideration only for large inputs. So as the input size is increasing, the runtime is also increasing drastically. Initially at 0 everything is same. Now when we increase the input size somewhat, this is the cubic function which is increasing very drastically, in a very higher rate, and we can see quadratic is also increasing in this way. This is logarithmic and this is the linear. So this is somewhat, I mean in a good way we can consider this linear one. There is somewhat difference in this graph. It is an exercise for you to understand what is it. And coming to runtime calculations, you might now, till now we discussed big O of n square. We compared big O of n square, which is greater, n is or n square, which is having higher growth rate. N square is obviously having higher growth rate, and neglecting constants, ignoring constants, and neglecting lower terms. Like if we have n plus n square, we neglect n and we only consider big O of n square. That is what we discussed. Now we will be discussing how that big O of n came, how that big O of n square came, how we calculate that based on the size of the input, how we calculate that. We will be discussing that. So here big O is an upper bound, right? As we discussed earlier, big O is upper bound, omega is lower bound, theta is average bound. So big O is an upper bound. Answer provided is based on big O notation is upper bound. Answer provided is guarantee that program will terminate within a certain time period. The program may stop earlier than this but never later, right? As it is a upper bound, the provided is guarantee that the program will terminate within a certain time period. The program may stop earlier than this but never later. So that is what the meaning of upper bound. Let's calculate the time complexity of this simple program. This calculates, if there are n elements in the array, it calculates sum of cubes of all elements in the array. So now consider the array input size is n. Okay, it is the array input size. Or we need to calculate the sum of first n cubes. Okay, so 1 to n. Now to calculate that, we are using a single for loop. This initialization, this declaration takes unit amount of time, this takes unit amount of time, this return takes unit amount of time, and here we can see this star takes unit amount of time, this star takes unit amount of time, this plus take unit amount of time, this assignment takes unit amount of time. Totally in this loop there are 4 unit amount of times, right, which sum up to 4. Now this 4 is executing n times, right, it is executing n times, plus 2 of unit times is the sum equal to declaration and this to return, so 4n plus 2. Now you might be getting a doubt that we are initializing here as well and we are comparing here as well, we are incrementing here as well, doesn't I mean, will it don't make any changes? It will, definitely it will, but it won't affect the big O notation. If we consider it, it will be like 6n plus 4 or 6n plus 5, like that. It will be somewhat like 6n plus 4. Then in case of big O notation, big O of 4n plus 2 is big O of n, big O of 6n plus 4 is is similar to big O of n only. So then it in big O notation they both are same, right? So to calculate every, I mean, how for every assignment, for how for every increment the time is varying, you can get it from this para. Okay, if you read this para, it will be very clear for you. Now let's discuss about general rules. Here we multiplied this 4 with n because this for loop is running for n times, right? It is having n iterations, so that is why we did it for n times. Okay. Now the general rules are: rule 1 for loops. In case of for loops, we calculate time complexity based on number of iterations. If it is a single for loop, number of iterations are n, so we can directly say that the time complexity is big of n. If it is nested loops, which means there is a for loop here and there will be another for loop here as well inside that for loop, which means for single iteration of outer for loop, the inner for loop will execute n times. For second iteration, it will execute n times. For third iteration, it will execute n times. For fourth iteration, it will execute n times, which is of n plus n plus n plus so on n times, which is equal to n square. So this is also number of iterations, but there is behind it, we need to derive it using mathematically. So when I equal to 0, this having n iterations, when I equal to 1, this having n iterations, while sum up all, it will be n into n, which is big of n square, right? Now the consecutive statements having for loops side by side. Here it is single for loop which is having big of n. It is two for loops which is having big of n square. Now I mean, sorry, not big O, one second, I will correct it. Which is of n iterations, it is having n square iterations. Now we will be doing n plus n square, and we neglect this lower term and we only consider big O of n square. This is what our final time complexity. Make sense? In case of if condition, to checking the condition and to checking the assignment operators, it takes unit amount of time, and for else it takes unit amount of time. If the S1 is having a for loop, then it will be taking big of n, or if S2 is having a nested for loop, then it will be taking big of n square. It depends upon S1 S1 runtime and S2 runtime. Okay, so recursion. Coming to recursion, when we are solving some problems using recursion, there it will be feeling somewhat tricky to calculate time complexity of recursion. Now let's see the recursion program for factorial. In case of factorial, we will be calculating this as n into factorial of n minus 1. If we do factorial of 5, if we calculate factorial of 5, which is 5 into 5 minus 1, which is 4, 4 into 4 minus 1, which is 3, 3 into 3 minus 1, which is 2, 2 into 2 minus 1, which is 1, and we stop it as base case at when n less than or equal to 1, we return 1, that's it. So it is executing n times, right? If we give factorial of 5, it is executing 5 times, right? So for this, it will be big of n only time complexity, because it is executing n times. Okay, it is having n recursion calls, and each recursion call it is of only one unit amount of time complexity, right? So it is big of n. In case of Fibonacci numbers, if this is the program for Fibonacci numbers, you might be seeing that there are two recursion calls. I mean, in each recursion call there is two recursion calls. You might be thinking it is 2n. No, it is not 2n. It is an exponential growth. It is 2 power n. It is 2 power n, very high time complexity. It can't run more than 30. If n is greater than or equal to 32, around that, it won't be executing efficiently for larger inputs. So why it is exponential? If you consider this f of 4, it will be calculating for f of 3 and f of 2. Now again for f of 3, it calculates for f of 2 and f of 1. Similarly for f of 2, it is again f of 1, again f of 0. Now you can see f of 2 is computed 2 times. This is for only small input 4, but if you consider for n as 30, 40 for larger inputs, there will be multiple repeated computations happening. So at every state we are having 2. So at every state it is dividing into 2. Make sense? So there is two kinds of, if the iterations are multiplying every time twice, initially it is 2, then it becomes 4, then it will become it will be having 2 again, it will be having 2 again, it will become 8 after 16. So it is forming a complete tree, right? Complete binary tree. So in that case we can consider number of nodes in that, which is 2 power n, like height of trees and number of divisions happening is so we can consider it as time complexity as big of 2 power n. You can derive these time complexities based on recurrence relations as well. So this is the recurrence relation for the above for this above program, which is t of n minus 1 plus t of n minus 2 plus 2. So this is n minus 1, n minus 2. So we can calculate this. How to calculate this is shown here. You can get this after doing this. You will be getting the time complexity as 2 power n only. And you need to observe this thing, the compound interest rule. Every time initially it is having only 1, after that we are having 2, again it is multiplying with 2, which is become 4, after that it is growing very exponentially, right? 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. That's why we call it as 2 power n. Now solution for maximum subsequence sum problem. There are multiple solutions as we discussed, n cube, n square, n log n, right? So if we consider this is an n cube problem. There are 3 for loops which are nested for loops, and this takes, if you consider these two for loops, these two inner for loops, it will be taking n square time complexity. Why? Because it is having n iterations, n minus 1 n plus n minus 1 iterations plus n minus 2 iterations plus n minus 3 iterations plus so on until 1. If we add all these things, we will be getting n square. We will be getting n square, and finally there is an outer for loop which executes n times, which means this n square executes n times, which means we need to multiply it into n finally, which is equal to big of n cube. Makes sense, right? It is in the terms of big of n cube. These are the mathematical calculations. Finally, this is the equation we will be getting. We will be ignoring the lower terms and constants. Finally, we will be getting big of n cube. That is the time complexity we will be having. Now there is a solutions for big of n square and log n as well. So this is the time complexity, runtime of big of n square. There is one for loop, there is another for loop. This for loop having n iterations. This for loop is also having n iterations. So for every iteration of outer loop, the inner loop execute n times. So which means n plus n minus 1 plus n minus 2 plus n minus 3 plus so on, sum up to n square. Makes sense? So the time complexity will be big of n square. Now this is the logarithmic code, I mean n log n, linear logarithmic n log n. So it will be somewhat difficult if you go. It is very easy to understand these codes. This is n square code and n cube code. It is very understand too easy this code by dry running, by running the code on piece of paper, and easy to estimate the time complexity or runtime as well. But in case of this logarithmic code, it looks somewhat complex. It uses the concept of divide and conquer. So I am not explaining this program, which will be taking very long time. It will be very confusing as well. So divide and conquer generally having time complexities of n log n. Okay, so this is also having n log n time complexity, which is base 2, which means now if we add an array, or if we add an n, we divide n with n by 2 and again n by 2. Now we divide it n by 2 again, which becomes n by 4, n by 4, n by 4, n by 4. Number of computations in this will be log n, because the height of the tree, we will be considering the height of the tree, which is log n. Okay, so in each term we are doing big of 1, so height of the tree will be log n. So every time we divide it, initially we used to multiply it with 2. So in that case it is happening 2 power n. If we divide it with 2, then it is log n base 2. If we divide it with 3, like n by 3, n by 3, n by 3, and n by 9, n by 9, n by 9, like that, then it will be log n base 3. If I divide it with k, then it will be log n base k. That is it. Now this is the recurrence relation for that, which is 2 into t of n by 2. In every recursion call, we divide the size of the array into size of the array to 2. That is, and I mean after that calculating the recurrence relations, it is n log n. You can find a similar recurrence relation in merge sort algorithm. Okay, so that is why the complexity of merge sort will also be n log n only. You will be learning all these things when we deep dive into the concept. Now this is the efficient one. This is called cadence algorithm, which is using linear time. We checked n cube, we checked n square, we checked n log n. Now we are checking n. We came to n, which is the efficient one. This is called cadence algorithm. So it is having only n iterations here. So in this will be taking the unit amount of time. It will be 4 or 5. It will be 6. Like if you consider 1, 2, 3 checking, 4, 5, 6. So it will be having 6 unit amount of time, and it will be n iterations. So it will be 6n. If we do it, it will be big of n, because we take this constant away. It is big of n. If you want to understand this algorithm, you can read this para, or you can dry run this code on a piece of paper with taking an example. With taking some example, it will be very clear. Logarithmic in running time. So generally there are two cases where we will be encountering logarithmic time complexities, which is of divide and conquer. One is the binary search, and sorting also comes under divide and conquer, so it will be considering a divide and conquer only, and the other is binary search. So in case of divide and conquer as well, we divide them and finally we merge them. So that is the meaning of divide and conquer. So if we divide it by 2 times in every stage, then it is log n. It is log n base 2. If we divide it 3 times every stage, it is log n base 3. In case of binary search, binary itself represents, binary means 2. So in binary search, every time we divide it based with 2 by 2. So binary search will also be having logarithmic time complexity. So this is the general standard code for binary search. I will just explain the intuition behind the binary search. See, to apply what is the need of binary search? We use binary search to find an element in an array. Yeah, in logarithmic time. To do that, the first and foremost step, it should be the array should be sorted. Okay, and the second after sorting the array, we will be landing at mid. We will be having 2 variables, one is low and one is high. Low will be assigned to 0, high will be assigned to n minus 1. we will be landing at mid. If we found the element at mid, we will be returning there only. If we didn't found, we compare it. If the current element is less than mid, then we need to okay, if the current element is less than mid, we need to move left side, which means this side. If the current element is greater than mid, then we need to move right side, and after moving to right side, we need to divide this right array into half again. After moving to some this side, we need to divide this part into half again. That is what we will do, dividing half again, and finally we will be getting log n time complexity. So this is of binary search. Now there is an algorithm called Euclid's algorithm to calculate GCD. This code looks very simple, and it is nothing but just replication of GCD how we calculate on paper. If we want to calculate GCD of 5 and 7, what we do? We write 5 here, we write 7 here, we calculate 5 ones are 5, which is 2 here. After 5 we will be writing here, again we 5 2 2 are 2, which is 4. Again we calculate 1 here, which is the GCD of 5 and 7 is 1. This is how we calculate GCD. Just this algorithm is converted into code. This is that code. So the time complexity is, if we are calculating GCD of m and n, then the time complexity will be log of max of m comma n. So for that, the proof will be like here. You can refer to this for this proof why this time complexity is achieved, log of max of m comma n. Okay, so this is the code for calculating GCD, which will be having time complexity of log of max comma log of max of m comma n. Okay, so the final concept today we are discussing into power, I mean exponentiation. If we want to calculate the power of, if you want to calculate a power n, what you will be doing? You will be multiplying a into a into a into so on n times. So it will be taking big O of n times, big O of n as a runtime. Okay, not that. If we use some concept called recursion, then you can do it in log n time only. How can you do that? So what will be happening is a of n, right? If n is even, we can write a of n by 2 into a of n by 2, right? So these two are similar terms. And if n is odd, we can write it as a into a of n by 2 into a of n by 2. So we can just put this in a recursion, and again n by 2 divides into two parts, again n by 4 based on whether it is even or odd. So this is the recursion call for that. If n is even, we are checking power of x into x. If we combine this, which is a into a whole power n by 2, right? We are doing x into x, we are passing again n by 2 as recursion. In this case of odd, we are doing x in a into a, passing n by 2, and finally we are multiplying a again. These are the base conditions in recursion. Okay, these are the main logic in recursion. The output is our assumption. So the time complexity will be n log n base 2. Here is the proof for the time complexity as well. These are the recursion call functions we can do in the single step recursions. So that is what the concept for today. I feel it is very much clear for you. If you have any doubts, you can go through the video again. You can pause it and you can write on your own, and if you feel uncomfortable, then also you can refer to the passages on the book which I mentioned. Most of the things I explain, and some time I suggest you to read the book to make it more clear. I hope this lecture will help you a lot to understand the concept. Thank you.